notes for 12.3, semicircles, interiors, and exteriors of circles. So in 12.2 we looked at circles, how we can define them in terms of points and distances, and then we looked at how we can write them from an algebraic equation in terms of x and y. What we'd like to do today is we'd like to look at a semicircle or half a circle, and then the interior of circles and exterior of circles. So at this point, if you haven't done so already, make sure you stop the video, read through example 1 on page 810 and 811. It kind of is very similar to what I'm going to talk about here, but that'll give you a little bit of a base to work from as we go forward. Alright, so let's take a look at number 1 here. It says, for the situation in example 1, the one that you just read, suppose that the passageway is 10 feet wide and 12 feet tall with a semicircular arch at its top. Also suppose the x-axis represents the floor with the origin at the center of the passageway. So what I've done is I've kind of set up that drawing, and we've got 10 going across here because that's what the opening is. I've got my origin at the center of the floor there at 0, 0. The height of the doorway is 12 feet, which means that this point right here, which would be the center of my semicircle, is at 0, 12. Okay? So the first thing I'm going to do is I'm going to do just like the first example, in that we're going to want to what is an equation for the semicircle representing the arch. So we want to get an equation for that semicircle. So let's do that. To do that, what I'm going to do is my center is 0, 12. And the radius of my circle is, well, I know it's 10 across here. This distance here is 10. Therefore, the radius of that circle has to be 5 units. Okay, so R is 5 because the diameter is 10. Therefore, the equation that I can write for that is x minus 0, or just x squared, plus y minus 12 squared is equal to r squared, or 25. So that would be an equation representing that semicircle, and of course we'd only be interested in the positive values from that. So to do that, if I'm more interested in the positive values, I want to solve that for y. So I'm going to bring x squared over to the other side. So I have y minus 12, quantity squared, is equal to 25 minus x squared. And then if I take the square root of both sides, I'm sorry, so this would actually be y minus 12 is equal to the square root of 25 minus x. And really at this point now, since I'm not squaring it anymore, I don't need those parentheses. So now I can add 12 to both sides. Therefore, and because I took the square root, it would be plus or minus this. So I can say y is equal to, well, I'm really only interested in the positive value, so I don't have to worry about the minus 1. So I'm just going to put the square root of 25 minus x squared plus 12. So this would represent an equation for that semicircle. And then if I wanted to find out the height, what this height would be right here, where this is 2 units from the center, we'll define that height. Basically, I'm gonna take the value for x equal to 2 and solve. So if I do that, if I plug x equals 2 in here, I get y is equal to the square root of 25 minus 2 squared, or 4, plus 12. So y is equal to 12 plus the square root of 21. And that would be an exact value, and we could get an approximation to that as well, which is about 16.6 feet. Next, we're going to talk about the idea of interiors and exteriors of circles. Every circle can be separated by the plane into into two regions. The regions inside the circle are called the interior of the circle. The region outside is called the exterior of the circle. The circle itself is a boundary between these two regions and is not part of either region. Okay? The interior and exterior of a circle theorem says that let C be the circle with center HK and radius R. Then the interior of this circle can be described as x minus h squared plus y minus k squared is less than the radius squared, and the exterior is the exact same thing but greater than the radius squared. So if we take a look at number 2 here, where it says graph the points that satisfy x minus 3 squared plus y plus 2 squared is greater than 5. So we're going to graph all the points that are outside the circle. So let's do that. Alright, so I'm going to start by just graphing the center point, which is at 3, negative 2. And then my radius squared is equal to 5. So if the radius squared is equal to 5, that means that r is equal to the square root of 5, which is approximately equal to 2.2, a little bit more than that. Okay? But 2.2 will work for this purpose. So what I'm going to do now is, from this point, just to get an idea what that circle looks like, I'm going to go approximately 2.2 units in this direction, 2.2 units up, 2.2 units to the left, and 2.2 units down to get kind of 4 points to help me get a gauge of what my circle looks like. Now, not going to be a perfect circle. I've got it kind of as a dotted circle because I know that that boundary is not going to be part of my solution set. And then it's going to represent all of those points that are outside of that circle on the exterior because it says greater than. So I'm going to just shade in anything out here on the outside of that circle. And that would represent my solution set. So everything on the outside of that circle. Okay? Take a look at number 3 then. It says a washer has an outer diameter of 25 millimeters and an inner diameter of 8 millimeters. Write a system of inequalities describing the area of the flat face of the washer. Approximate the area of the flat face of the washer to the nearest tenth of a square millimeter. Okay, so let's just kind of first draw a picture of that. We've got this washer. It's got an outer ring and an inner ring. The outer ring has a radius of, the diameter is 25, so the radius is 12.5. And the inner ring has a radius of, since the diameter is 8, the radius is going to be 4 millimeters. This would be millimeters as well. Okay? So we want to know, it says write a system of inequalities describing the area of the flat face of the washer. Approximate the area of the flat face of the washer to the nearest tenth of a square millimeter. Okay, so if the inner one has a radius of 4 millimeters, I know that if and I'm just going to say that the center of the washer is 0, 0. If that's the case, I could say that if I were just to write an equation for that inner circle, I would say it's x squared plus y squared is equal to 16. Okay, 4 squared. But I know I'm looking at the area which is greater than that, because that wouldn't be an open circle. So in terms of an inequality to represent that, I would say x squared plus y squared has to be greater than 16. And then if I looked at the outer circle, well, I can say that's x squared plus y squared is equal to 12.5 squared, which is 156.25. And once again, we're not talking about equal here because that's the outer edge of it, so I want the stuff that's less than that. Okay, so the area is represented by everything where x squared plus y squared is greater than 16, and x squared plus y squared is less than 156.25. Well, to find that area, the area would be equal to the area of the larger circle, which is pi r squared of the larger. So for the larger circle, that would be 156.25 is r squared, so it would be 156.25 times pi minus the area of the smaller circle. Well, the area of the smaller circle would be pi r squared as well, but this time my r is 4, therefore r squared is 16, so it would be minus 16 pi. Okay. Which is equal to, if I can combine those, they're like terms, so that would be 140.25 pi. And then it's approximate to the nearest tenth of a square millimeter. This is square millimeters here, so I need to multiply that out. So on my calculator, I'm going to do that. So I've got 140.25 times pi. And I want to get an approximation, so I'm going to hit Control Enter, which gives me 440.608. It said to the nearest tenth, so what was that again? 440.608. 440.6 square millimeters. And that would be the answer.